Hello there, and welcome to the Sleepy Space Channel. Every illustration you have ever seen of the space beyond Pluto is wrong, and it is wrong in the same direction every time. The belts are drawn crowded, and they are not. The typical distance between two objects out there is greater than the distance from the Earth to the Sun. Past 30 astronomical units, the Sun stops being a disk at all and becomes simply the brightest star in the sky. And somewhere past 100, the inside of our own solar system turns out to be emptier than the space between the stars. Tonight we travel outward along that direction slowly and watch every measure of emptiness grow more extreme the further we go. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Nothing out there is in motion toward anything. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. There is no line. The phrase "beyond Pluto" suggests that somewhere out there a line has been drawn. It suggests a threshold, a marker, a place where one thing stops and another begins. The solar system does not work that way, and the first honest thing to say about the space past Pluto is that there is nothing there to cross. No boundary was ever laid down. No instrument on any spacecraft has ever registered the moment of passing out of the familiar solar system and into the unfamiliar one, because that moment does not exist in any form an instrument could detect. Pluto itself is a useful place to begin, because Pluto does not sit where most people imagine it sits. It orbits at an average distance of about 39.5 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers, so Pluto's average distance works out to something near 5.5 billion kilometers. That is a number the mind slides off. It helps to convert it into time instead. Light, which crosses the distance from the Sun to the Earth in a little over 8 minutes, takes about 5.5 hours to reach Pluto. The orbit is not a circle. It is a pronounced ellipse, and the difference between its two ends is large enough to matter. At its closest approach to the Sun, Pluto comes in to about 30 astronomical units. At its furthest, it recedes to roughly 49. The consequence of that stretch is a fact that still surprises people who have not thought about it recently. For about 20 years out of every orbit, Pluto is closer to the Sun than Neptune is. During those 2 decades, the outermost planet is not the outermost object, and the ordering everyone learned as children quietly reverses itself. The two never come near each other. They cannot. Pluto and Neptune are held in what astronomers call a 3-to-2 resonance, which means that Pluto completes exactly 2 orbits in the time Neptune completes 3. That ratio is not a coincidence, and it is not fragile. It is a locked arrangement maintained by gravity itself, and the geometry it enforces guarantees that whenever Pluto arrives at its closest point to the Sun, Neptune is somewhere else entirely, far around the other side of its own path. The two bodies have been performing this arrangement for billions of years and have never come within 17 astronomical units of one another. Pluto's path is also tilted. It leans about 17 degrees away from the flat plane in which the 8 planets do their orbiting, which carries Pluto well above that plane for part of its circuit and well below it for the rest. This matters for the shape of the story we are telling tonight, because it means that even the last of the classical worlds does not really belong to the neat disk we draw when we draw the solar system. Pluto spends most of its time outside the lane. So there is no line at Pluto. There is only a small, cold, complicated world moving slowly along a tilted ellipse, and the space around it was already almost entirely empty long before anything arrived to notice. Consider what it takes to get there. The fastest spacecraft ever launched from the surface of the Earth left at a higher speed than any object before it, on a path aimed directly out of the solar system, and it still borrowed a gravitational push from Jupiter along the way to go faster still. Even with every advantage, the journey to Pluto's distance took 9.5 years. During that flight, the spacecraft spent most of its time asleep, because there was nothing along the way worth staying awake for. That detail is worth holding on to, because it is the shape of everything that follows. The journey was not dangerous. It was not eventful. It was simply long, and almost entirely without incident, and the reason for that is the same reason we are here tonight. The space is empty in a way that is difficult to picture from the surface of a crowded planet. There is one more property of this region that deserves saying before we go further out, and it concerns communication. A radio command sent from Earth toward Pluto takes about 5.5 hours to arrive. The reply takes as long again. Nothing out there can be operated in any ordinary sense. A spacecraft passing through that region is not being flown. It is executing instructions written down years earlier and stored in its memory, and by the time anyone on Earth learns whether an instruction worked, the moment it applied to is most of a day in the past. That delay grows steadily with distance, and it never stops growing. At 100 astronomical units, a signal takes almost 14 hours in each direction. Everything anyone has ever learned about the far solar system arrived late, and will always arrive late, and the lateness is not a limitation of the equipment. It is a property of the space. We tend to imagine the solar system as a place with a shape and therefore with a border. It is far more accurate to imagine it as a fading. The sun's light fades with distance. The sun's wind fades with distance. The sun's gravitational authority fades with distance. All three fade at different rates, and none of them stop anywhere in particular. What we call the solar system is simply the volume in which those three influences are still the loudest thing present, and the volume in which that is true has no wall around it. Beyond Pluto, then, is not a destination. It is a direction, and the direction continues for a very long way. For the next 2 hours we are going to travel along it slowly, and at each stage we are going to look at what the emptiness is actually made of, because it turns out that emptiness is not one condition. It is at least 6 of them, each measured differently, and every one of them gets more extreme the further out you go. It is worth being precise about the scale of that 5.5 billion kilometers, because the number by itself does very little work. If the sun were reduced to the size of a common doorway, the Earth would be a small marble about 25 meters away, and Pluto would be a grain of coarse sand roughly a kilometer distant. Every planet in the solar system would fit comfortably inside that kilometer, and almost all of the space between the doorway and the grain of sand would contain nothing whatsoever. That is the model of the solar system that nobody draws, because it cannot be drawn. Any illustration that shows the planets at a useful size must compress the distances, and any illustration that shows the distances honestly must reduce the planets to invisibility. We have never had an accurate picture of our own solar system available to look at, and the picture we do have is wrong in exactly the direction that makes the emptiness hardest to imagine. There is a further reason the mind resists this, and it has to do with how the region was named. The outer solar system carries a great many names: the Kuiper belt, the scattered disk, the heliosphere, the Oort cloud, and every one of them is a noun. Nouns suggest things. They suggest structures with edges and interiors, places you could arrive at and be inside of. In practice, each of those names describes a statistical tendency rather than an object, a region where a particular kind of body is somewhat more likely to be found than in the regions on either side. The names are useful, and they are not misleading to the people who use them professionally, but they carry an implication of substance that the regions themselves do not possess. Something similar applies to the maps. Every diagram of the outer solar system shows orbits as solid lines, and solid lines look like tracks, like the rails of something built. An orbit is not a track. It is the record of where a body has been and a prediction of where it will go, drawn in a place where there is nothing at all. If you traveled to the position of one of those lines, you would find no marker, no material, no indication of any kind that anything passes through. The lines are the most conspicuous feature of every diagram, and they are the one thing in the diagram that does not exist. Hold those three corrections together, the compressed distances, the solid-sounding names, and the drawn-in lines, and something becomes clear about why the emptiness out there is consistently underestimated. It is not that people have been told the wrong facts. It is that every tool we use to represent the region has to add something to it in order to show it at all. We begin with the one most people get wrong. Part 2. The belt that is not a belt. Almost everyone carries the same picture of the Kuiper belt, and almost everyone acquired it from the same source. It comes from illustrations. In the illustrations, there is a broad grey band encircling the outer solar system, thick with tumbling ice and rock, dense enough that a ship crossing it would need to pick its way through. That picture is wrong, and it is not wrong by a small margin. It is wrong by a factor so large that correcting it changes the character of the entire outer solar system. The classical Kuiper belt occupies a region running from roughly 30 astronomical units out to about 50. It is a torus, a thickened ring, made of icy bodies left over from the construction of the solar system. Estimates of how many of those bodies exceed 100 kilometers across generally run to something over 100,000. That number sounds like a crowd, and this is precisely where the intuition fails, because the number of objects means nothing until it is set against the volume they occupy. Consider the volume properly. A sphere 50 astronomical units in radius, with a sphere 30 astronomical units in radius removed from the middle of it, encloses something on the order of 400,000 cubic astronomical units. A cubic astronomical unit is a box 150 million kilometers along every edge. It is difficult to hold that in the mind, so hold this instead. One of those boxes could contain the entire orbit of the Earth around the Sun, with room to spare on all sides. Now distribute 100,000 objects through 400,000 of those boxes. The arithmetic gives roughly 4 such boxes for every object. Work that back into a typical separation, and the answer comes out at more than 1 astronomical unit between neighbors of any appreciable size. The bodies of the Kuiper belt are, on average, further apart from one another than the Earth is from the Sun. The consequence of that spacing is the single most important thing to understand about the region, and it deserves to be stated as plainly as possible. If you were standing on the surface of a Kuiper belt object, you would not be able to see the Kuiper belt. There would be no band across the sky. There would be no ring overhead, no drifting boulders, no sense of being inside anything at all. There would be one dark, cold body under your feet, and above it an unbroken field of stars, and among those stars one that was noticeably brighter than the others. That is what the belt looks like from inside it. It looks like nothing. This is why no spacecraft has ever needed a collision avoidance plan for the Kuiper belt. Mission planners have never once had to consider the possibility of an impact while crossing it, and the reason is not that their shielding is good. The reason is that there is essentially nothing to hit. The probability of encountering anything at all, on any trajectory through the region, rounds to 0. The same error, made at smaller scale, has already been corrected once in the public imagination. The asteroid belt between Mars and Jupiter is drawn the same way as a dense field of tumbling rock that has to be threaded carefully. In reality, the entire asteroid belt contains a total mass smaller than the Moon, spread across a volume so large that every spacecraft ever sent through it has passed without any evasive maneuver whatsoever. Some of those spacecraft went looking for asteroids to photograph and had to aim carefully to find one. The Kuiper belt is that same misunderstanding, repeated at 20 times the distance and across a volume thousands of times greater. It is worth spending a moment on what actually lives out there, because the population is not uniform. It divides into groups, and the groups have different histories. The resonant objects hold orbits mathematically tied to Neptune's, in the same way Pluto's is. The largest group among them completes 2 orbits for every 3 of Neptune's, exactly as Pluto does, and for that reason they are called Plutinos. They are not a family in the sense of having a common origin as a single broken body. They are a family in the sense of sharing a rhythm, held in place by the same gravitational arrangement that protects Pluto. The classical objects sit further out, mostly between about 42 and 48 astronomical units, on orbits that are gentler and more nearly circular. These are sometimes called cubewanos, after the designation of the first one identified. They are the most undisturbed population in the region, and many of them appear never to have been moved from where they formed. The scattered disk objects are the ones that were thrown. Their orbits are steep, tilted well out of the planetary plane and enormously elongated, carrying them from somewhere near Neptune's distance out past 100 astronomical units and slowly back again. They are still, loosely, under Neptune's influence, and their orbits are still very gradually changing. Each of these populations shares the same essential property. However you sort them, the objects are separated by distances that make the idea of a belt meaningless. The word belt implies something you could be inside of. The Kuiper belt is a statistical description of where objects are slightly more likely to be found than elsewhere, and nothing more than that. There is one further correction worth making, and it concerns thickness. The illustrations show a thin, flat band. The real distribution is much thicker than it is drawn, extending well above and below the planetary plane, because many of the objects have inclined orbits. That thickness makes the volume larger still, which makes the spacing wider still, which makes the emptiness deeper still. Every correction to the picture points in the same direction. Notice what has already happened to the word we started with. When most people hear that the space beyond Pluto is empty, they imagine a quantity of nothing, as though emptiness were a simple absence you could measure once. It is not. The emptiness of the Kuiper belt is a particular kind of emptiness, with a particular number attached to it, and that number is a separation of more than 150 million kilometers between neighbors. Hold that image of standing on a dark surface under unbroken stars, because we are going to return to it at the end of the evening, from very much further out. There is a way to make the spacing concrete that works better than the arithmetic, and it involves thinking about what it would take to see anything at all from out there. Suppose you were standing on a classical Kuiper belt object, and there happened to be a neighboring body of similar size at the typical separation. Call it 1.5 astronomical units away, something over 200 million kilometers. That object is perhaps 200 kilometers across. At that distance, it would subtend an angle of well under 1,000th of a minute of arc, which is to say, it would be far smaller than the finest detail any eye can resolve. It would not be a shape. It would be a point, and it would be an extraordinarily faint one. It is being lit by a sun delivering 1/1600th of the light that falls on Earth, and it is reflecting only a fraction of that, across a distance greater than the one separating us from our own star. The result would be a speck considerably dimmer than the faintest stars visible on a dark night from a dark place. Your nearest neighbor in the Kuiper belt would be harder to see than most of the stars behind it, and you would have no way of telling which of the dim points in your sky was a body 200 million kilometers away and which was a sun thousands of light years distant. That is worth sitting with, because it dissolves the last remnant of the belt image. It is not simply that the objects are too far apart to form a visible band. It is that even if you knew exactly where to look, and looked with a clear eye from a dark surface, you would not be able to pick your nearest neighbor out from the background at all. The same reasoning applies to the material we do not count. Between the large bodies there is dust, and there are fragments, and there are objects a meter or a kilometer across, in numbers nobody can estimate well. All of it is real. None of it is dense enough to matter. A spacecraft crossing the region at 14 kilometers per second, with a cross-section of a few square meters, traveling for a decade, is expected to encounter essentially nothing, and in practice has encountered essentially nothing. The dust detectors register occasional impacts from grains too small to see, arriving at a rate of a few per day. That is the entire traffic of the Kuiper belt, as experienced by something moving through it. So the correction to the illustrations is not a matter of degree. The illustrations show a region full of material. The region contains, from the point of view of anything passing through it, an unbroken emptiness interrupted a few times a day by a particle smaller than a speck of smoke. And there is a second question hiding inside the first one, which we turn to next. The material out there is not merely sparse. It is far sparser than it should be, given what is known about how those objects came to exist. Something removed almost all of it. Part 3. The missing mass. The emptiness of the outer solar system is not an original condition. It was produced. Something happened out there, long ago, that took most of the material away, and the evidence for that event is written into the discrepancy between two numbers. The first number is the present-day mass of the Kuiper belt. Adding up everything currently believed to be out there, the large bodies, the small bodies, and the estimated population of objects too faint to have been counted individually, gives a total of only a few % of the Earth's mass. That is a small fraction of one small planet, distributed across billions of kilometers of space. It is very close to nothing. The second number comes from asking how those objects could have formed in the first place. Bodies several hundred kilometers across do not simply appear. They grow, slowly, by accumulating smaller material through gentle collisions over a very long period. That process has requirements. It needs a supply of raw material dense enough that encounters happen often enough to matter, and it needs that supply to persist for a considerable time. Run the calculation with the amount of material currently present, and the answer is unambiguous. The objects we observe could not have grown there. There is not enough left, and there is not nearly enough left, and no reasonable adjustment closes the gap. Working backward from the sizes that actually exist gives a starting disk of something in the region of tens of Earth masses in the same volume of space. Some estimates place it lower and some higher, but every serious version of the calculation lands in the same territory. The region needed to begin with many times the mass of the Earth in order to end up with what is there now. Set those two numbers beside each other. Tens of Earth masses at the beginning. A few % of one Earth mass today. The overwhelming majority of the original material, well over 99% of it, is no longer in the region where it formed. This is the point at which the emptiness stops being a passive fact and becomes the result of something. And the leading account of what happened is one of the more satisfying reconstructions in planetary science, because it explains several unrelated features of the solar system with a single event. The account begins with a claim that sounds unlikely until you look at the evidence for it. The giant planets did not form where they are now. In the early solar system, they sat closer together and closer in, embedded in a thick disk of leftover icy material extending outward beyond all of them. That configuration was not stable. As the planets interacted gravitationally with the surrounding debris, they exchanged orbital energy with it, and the exchange moved them. Neptune moved outward. It did not move quickly by human standards, but over tens of millions of years it migrated a considerable distance, and as it went, it dragged its gravitational resonances along with it. A resonance is a region where an object's orbital period stands in a simple whole number ratio to the planets, and where the repeated gravitational nudges therefore accumulate instead of cancelling out. Resonances are narrow, powerful, and they move with the planet that creates them. Picture Neptune's resonances sweeping outward through a disk of small icy bodies. Each resonance, arriving at a given radius, has one of two effects on the material it finds there. Some objects are captured. They fall into step with the resonance. Their orbits become locked to Neptune's rhythm, and they are carried outward along with it into protected arrangements they still occupy today. That is where the Plutinos came from, and it is where Pluto's own orbit came from. Pluto is not an oddity that happened to end up in a resonance with Neptune. Pluto is a survivor of a process that captured a great many objects the same way. The other effect is more common and more consequential. Most of the material was not captured. It was thrown. Objects that received a gravitational kick without being locked into a stable arrangement were flung onto new orbits, and the new orbits went in every direction. Some went inward, into the region governed by the other giant planets, where they were either absorbed by a collision or handed onward, and eventually ejected from the solar system altogether. Some were thrown into long, steep ellipses that carried them far out and slowly back, and those objects are the scattered disk we can still observe today. And a great many were thrown so hard that they never came back at all, out to distances thousands of times further than where they began. That is where the missing mass went. It was not destroyed, and it did not evaporate. It was relocated from a region that was moderately empty into regions that are very much emptier, by a planet that was itself in the process of moving. There is a way of stating this that captures the whole part in one sentence, and it is worth stating carefully. The outer solar system is not empty because nothing was ever there. It is empty because almost everything that was there was moved somewhere emptier. The scattered disk is the visible residue of that upheaval, and it repays a closer look. Its members occupy orbits that no undisturbed population would ever have. Their paths are inclined at large angles to the plane the planets share, sometimes very large angles. Their eccentricities are extreme, which means the difference between their closest and furthest points from the Sun can be a factor of several. And crucially, their closest points still cluster near Neptune's distance, which is the fingerprint of the encounter that put them there. Those orbits are still slowly evolving. Every time a scattered disk object returns to the inner end of its ellipse, it passes back into Neptune's neighborhood and receives another small gravitational adjustment. Over sufficient time, some of them are pushed further out, some are pulled in, and a fraction are eventually removed from the solar system entirely. The process that emptied the region has never stopped. It has only slowed down because there is so little material left for it to work on. There is a quieter implication in all of this that deserves attention. The material out there, the objects that were captured rather than thrown, the classical bodies that were never disturbed at all, is not simply old. It is unprocessed. It has never been heated by proximity to the Sun, never been melted, never been compressed inside a larger body and reformed. It has been sitting in the cold since the solar system was assembled, holding a chemical composition that has not been meaningfully altered in more than 4 billion years. That is the compensation for the emptiness. What survived out there survived precisely because nothing else was close enough to interfere with it. And that connection between emptiness and preservation is going to keep returning tonight, in different forms, all the way to the end. There is a piece of supporting evidence for this account that comes from an unexpected direction, and it is worth including because it shows how much a single reconstruction can explain. If the giant planets migrated, and if that migration threw an enormous quantity of icy material in all directions, then some fraction of that material would have been thrown inward rather than outward. Inward thrown bodies would have crossed the orbits of the inner planets over a relatively short span of time, and a proportion of them would have struck those planets. There should therefore be a period in the early history of the solar system during which the inner worlds were hit far more often than before or after. The surfaces of the Moon and Mercury preserve exactly that kind of record because nothing has erased it. Craters accumulate on an airless, geologically quiet world at a rate that reflects how much material is crossing its orbit, and the ages of the largest impact basins cluster in a way that suggests a distinct interval of heavier bombardment several 100 million years after the solar system formed, rather than a smooth decline from the beginning. The interpretation is debated, and the dating carries real uncertainties, and honest accounts present it as suggestive rather than settled. But the shape of the evidence matches the shape of the prediction, and the same event that emptied the outer disk would have been visible on the inner worlds as a period of increased impacts. There is a second line of support that comes from the resonances themselves. If Neptune had always been where it is now, the objects in resonance with it would be a small population that happened to form there. If Neptune migrated outward, capturing objects as it went, the resonances should be far more heavily populated than chance would produce, and the captured objects should show a particular distribution of orbital tilts and elongations reflecting the capture process. That is what surveys find. The Plutinos are not a marginal group. They are a substantial fraction of everything catalogued in the region, which is very difficult to explain without something having gathered them. And there is a third consideration, which is simply about where the giant planets are. Models of planet formation have persistent difficulty producing Uranus and Neptune at their present distances, because the disk out there is too thin and the orbital periods too long for those planets to have grown to their observed sizes in the available time. Allowing them to form closer in, where material was denser, and then to migrate outward afterward, resolves that difficulty directly. Three independent problems: the cratering record, the overpopulated resonances, and the formation of the ice giants, all ease at once if the outer planets moved. That is the kind of convergence that makes a reconstruction persuasive, and it is why the migration account has held up as well as it has. Before we follow the thrown material outward, though, there is something at the far edge of the classical belt that nobody expected to find, and that nobody has yet explained. Part 4. The Cliff. Surveys of the Kuiper belt were designed with a straightforward expectation. A disk of leftover material, spread outward from a star, should thin gradually with distance. The density of objects should fall off smoothly, the way the outer parts of anything spread thin tend to fall off smoothly, with no particular radius standing out from its neighbors. That is what the models predicted, and it is a reasonable prediction, and it turned out to be wrong. What the surveys found instead was an ending. The population of classical Kuiper belt objects does not taper away with distance. It stops. At around 48 astronomical units from the Sun, the number of objects drops off far more sharply than any smooth model of a disk permits, and beyond that radius, the classical population very nearly disappears. The feature is called the Kuiper cliff, and the name is accurate. It is not a slope. It is a step. The first response to a result like this is always to suspect the instrument rather than the universe, and that suspicion was taken seriously. Objects further away are fainter, and fainter objects are harder to find, so a survey will naturally recover fewer of them at greater distance, even if the true population is unchanged. Correcting for that effect is routine, and it was done carefully. Surveys were then run that were deliberately sensitive enough to detect objects well beyond 48 astronomical units, at brightnesses that should have produced plenty of detections if the disk continued as expected. The detections did not come. Sensitive searches found only a small handful of classical objects beyond the cliff, where the models predicted a substantial population. The feature survived every attempt to explain it away as an artifact of looking. It appears to be a real property of the solar system, and it is one of the most conspicuous unexplained structures anywhere in our neighborhood. There are several accounts of what could have produced it. None of them is established, and it is worth going through them slowly and giving each one honest weight, because the situation here is not one where a leading answer is being politely resisted. It is one where several reasonable answers are all still standing. The first possibility is that the disk simply ended there. The cloud of gas and dust from which the solar system formed did not extend outward forever, and it may have had an outer limit near that radius from the beginning. In this account, the cliff is not the result of anything happening afterward. It is the original edge of the raw material, preserved. The second possibility involves Neptune's migration, which we spent the last part discussing. Neptune moved outward through the disk, and its resonances did the work of capturing and scattering material as they went. But Neptune's migration did not continue indefinitely. It stalled and stopped, and the radius at which it stopped is not far from the radius of the cliff. In this account, the material beyond that point was never properly delivered, never stirred, and never assembled into bodies of the size surveys can detect. The third possibility looks outside the solar system entirely, and it has a certain quiet force to it. Stars do not generally form alone. They form in clusters, dozens or hundreds or thousands of them condensing out of the same cloud within a relatively short span, and those clusters take tens of millions of years to disperse. Our Sun almost certainly formed in such a group. During that crowded early period, other young stars would have passed close by, far closer than any star has passed since. A star passing within a few hundred astronomical units of a young solar system does something specific to its outer disk. It does not disrupt the inner planets, which are held too tightly to be moved. But the outer material, only weakly bound, is stripped away or thrown onto orbits that carry it out of the system. The result is a disk with a truncated outer boundary, cut off at a radius determined by how close the passing star came. In this account, the cliff is a scar, left by a star whose name we will never know, which drifted away from our neighborhood 4.5 billion years ago and has been somewhere else in the galaxy ever since. The fourth possibility is that something large is out there, or was. A body of sufficient mass moving through the outer disk would clear a region around its own orbit, sweeping up or scattering the small objects it encountered, and leaving a boundary behind it. This account is often discussed alongside the question of undiscovered planets in the outer solar system, and we will return to that question properly later tonight. For now, it is enough to note that it remains one of the candidate explanations, and that it has neither been confirmed nor ruled out. There is a fifth consideration that complicates all four, and it comes from an unexpected source. A spacecraft crossing the outer solar system carries an instrument that counts impacts from very small dust grains, particles far too small to be seen by any telescope, produced by slow collisions between larger bodies. The count of those grains was expected to fall away as the spacecraft passed the cliff, for the simple reason that dust is produced by objects, and there should be fewer objects out there to produce it. The dust did not fall away as expected. It persisted further out than a hard cliff predicts, and the readings suggest that fine material continues well beyond the radius at which the visible population ends. There are two ways to read that. Either the belt does continue past the cliff in the form of bodies too small to be detected individually, which would mean the cliff is a boundary in the size distribution rather than in the amount of material. Or there is a second, more distant belt beyond the first one, separated from it by a genuinely emptier gap. Neither reading has been settled, and both would be interesting. The dust measurements are difficult, the population estimates carry large uncertainties, and the region involved is so poorly surveyed that a substantial revision remains possible. What can be said with confidence is this. There is a real feature at the outer boundary of the classical Kuiper belt, at a radius of roughly 48 astronomical units. It is sharper than a disk of leftover material has any obvious reason to be. It may be an original edge, or a stalled migration, or the mark of a star that passed by while the sun was young, or the wake of something large, or a boundary in size rather than in substance. The evidence does not currently distinguish between them. It is worth sitting with that for a moment, because it is a good example of something the outer solar system does repeatedly. The region is close enough to be studied and far enough to resist being understood, and the result is a set of questions that are genuinely open rather than merely unresolved in detail. Nobody is withholding the answer to the Kuiper cliff. The answer has not been obtained. It is worth describing how a survey of this kind is actually carried out, because the practicalities explain both why the cliff was hard to establish and why it has been so hard to explain away. Distant solar system objects are found by motion. A telescope takes a series of images of the same patch of sky over a period of hours, and everything genuinely distant, the stars, the galaxies, stays exactly where it is between exposures. Anything belonging to our own solar system shifts slightly, because the Earth has moved beneath it and because the object itself has moved along its orbit. A body in the Kuiper belt drifts by a small but detectable amount over a single night, and the drift rate is itself informative, because more distant objects move more slowly. The rate at which a point of light creeps across the frame is a direct measurement of how far away it is. That technique works well, and it has been applied to large areas of sky with progressively more sensitive instruments over several decades. The results consistently show the same thing: a healthy population of classical objects out to somewhere near 48 astronomical units, and then very little. The reason this could not be dismissed as a sensitivity limit comes down to a comparison. In the same surveys at the same sensitivity, objects were being detected at 45 astronomical units in substantial numbers. The step in brightness between an object at 45 and one at 55 is real but modest, a factor of a little over 2, given the fourth power law. A survey finding hundreds of objects at the nearer distance should find a meaningful number at the further one, if the population were continuous. It found almost none. There is one more twist that keeps the question from closing. Occultation studies, watching for the momentary dimming of a background star as an unseen object passes in front of it, provide a way to detect small bodies that are far too faint to image directly. Those studies are difficult, the events are extremely brief, and the detections are few. But they probe a different size range from the imaging surveys, and the results have not been straightforwardly consistent with a simple hard edge either. So the picture that emerges is not a clean one. There is a real and sharp reduction in the number of objects of imageable size beyond about 48 astronomical units. Whether that reduction extends to smaller bodies, and whether the dust measurements are telling us the material continues in finer form, and whether a second population exists further out separated by a genuine gap, are all open. Every one of those possibilities has support, and none has enough. That combination, a feature everyone agrees is there, and no agreement about what it is a fair description of most of what lies beyond Pluto. And past the cliff, whatever put it there, the emptiness continues. What changes past that point is not only how much material there is, it is how much light there is to see it by, and that turns out to be the deeper problem. Part 5. The light goes out. The second kind of emptiness beyond Pluto is an emptiness of light, and it behaves differently from the emptiness of matter. Matter out there is sparse but locally normal. An object in the Kuiper belt is as solid as any object anywhere. Light is not like that. Light thins continuously, everywhere at once, and it thins according to a rule so simple that its consequences are easy to underestimate. Sunlight spreads outward from the sun in all directions, and as it spreads, it covers an ever larger sphere. The surface area of a sphere grows with the square of its radius, so the same quantity of light must cover 4 times as much area when the radius doubles. The brightness, therefore, falls with the square of distance. At the distance of Mars, sunlight is less than half as strong as it is at Earth. At Jupiter, it is about 1/27th. At Pluto's average distance of 39.5 astronomical units, the arithmetic gives roughly 1/1600th of the light we receive here. That number is smaller than most people expect, and the experience it corresponds to is brighter than most people expect. 1/1600th of daylight is not darkness. It is comparable to deep twilight on Earth, the light you have about an hour after the sun has gone down, when colors have drained toward gray, but you can still see the ground clearly and could still read a page held close. Noon on Pluto is not black. It is dim, blue-gray, and perfectly adequate to see by. There is even a term for it among the people who studied that world closely, and the term is Pluto time, referring to the moment each evening when the light on Earth matches what Pluto receives at midday. So the loss of light out there is real, but survivable, and if brightness were the only measure, we could stop the part here. It is not the only measure, and the second measure is the one that matters. Along with brightness, distance takes away something else from the sun. It takes away its size. Any object seen from further away subtends a smaller angle in the sky. The sun, as seen from Earth, spans about half a degree, which is 30 minutes of arc, and which is why we experience it as a disk with a definite edge rather than as a point of light. That angular size falls in direct proportion to distance. From Jupiter, the sun spans about 6 minutes of arc. From Saturn, a little over 3. From Uranus, about 1.5. The human eye has a limit. Under good conditions, it can resolve a disk down to about 1 minute of arc, and below that limit, an object stops looking like a disk and starts looking like a point. It does not gradually blur. It simply becomes a star. Do the division and the answer arrives at a specific distance. The sun's angular size drops below 1 minute of arc at somewhere around 30 astronomical units, which is to say, at about the distance of Neptune, and comfortably inside the orbit of Pluto. This is the fact worth carrying out of tonight, and it should be said as directly as it can be said. From Pluto, and from everywhere beyond it, the sun is not a disk. It has no visible edge, no shape, no width. It is a point of light. It is a star. Consider what that removes. There is no daytime out there in any sense the word usually carries. There is no sunrise in which a body climbs above the horizon and takes up space in the sky. There is no glare that forces the eyes away, no shadow with a soft edge, no sense of a source you could point at and say that it has a size. There is a very bright star, brighter by a wide margin than anything else, and it moves across the sky as the world turns, and when it is above you, it is day. And the other stars do not go out. On Earth, the atmosphere scatters sunlight across the whole sky and drowns everything else, which is why our daytime sky is blue and empty. Out past Pluto, there is no atmosphere on most of these bodies worth speaking of, and no scattering, and therefore no distinction between the day sky and the night sky. The stars are present at all times. The sun crosses among them, the brightest object in a sky that never clears, and the constellations behind it remain visible the entire way across. The dimming continues past that point, and it continues according to the same rule. At 100 astronomical units, the sun delivers about 1/10,000th of the light it delivers here. At 1,000 astronomical units, 1/1,000,000th. At 10,000, 100,000,000th. The sun does not go out at any specific distance. It joins the general population of stars, gradually, and the only thing that distinguishes it at any given point is how much brighter it still is than the rest. There is a practical consequence of all this dimming, and it is the reason so much of the outer solar system remains unmapped. An object out there does not shine. It is seen only by reflected sunlight, and that sunlight has to make the journey twice, outward from the sun to the object and back from the object to a telescope near the Earth. Each leg of that journey costs the inverse square of distance. Both legs together therefore cost the fourth power. An object twice as far away is not 4 times fainter, as it would be if it were producing its own light. It is 16 times fainter. An object 3 times as far away is 81 times fainter. An object 10 times as far is 10,000 times fainter. This is a brutally steep penalty, and it dominates everything we know about the region. It means that the difficulty of finding objects increases far faster than the distance does. It means that a survey capable of detecting a body of a given size at 40 astronomical units would need to be 16 times more sensitive to detect the same body at 80, and 10,000 times more sensitive to detect it at 400. It also means that our census of the outer solar system is not a census of what is there. It is a census of what happens to be bright enough and close enough and positioned favorably enough to have been noticed. Objects on long elliptical orbits spend the overwhelming majority of their time near the far end of those orbits, where they are faintest and are only detectable during the brief portion of each circuit when they come closer. For an object with a 10,000-year period, that detectable window might be a century or two out of every 10,000 years, which means that for every distant object anyone has ever found, there are almost certainly a great many more currently at the far ends of their orbits, moving very slowly through the dark, entirely undetectable and entirely real. Part of what emptiness means out there, then, is unlit. The region is not merely sparse. It is sparse and dark and unreflective, and the darkness compounds the sparseness in a way that makes the two nearly impossible to separate. When we say the outer solar system is empty, we are describing something we cannot see, and we are describing it with instruments that lose their grip on it faster than the space itself expands. There is a further consequence of the sun becoming a point that is easy to miss, and it concerns shadows. On Earth, shadows have soft edges. The reason is that the sun is a disk rather than a point, so the edge of any shadow is a region partially lit by one part of the solar surface and blocked from another. That soft border is called the penumbra, and it is why a shadow cast by a tree becomes progressively less distinct the further the ground is from the branch. It is a familiar enough feature of daylight that most people have never registered it as a fact requiring explanation. Beyond 30 astronomical units, the penumbra effectively disappears. A point source casts a shadow with a hard edge. On the surface of a Kuiper belt object, the boundary between lit ground and unlit ground would be a sharp line, as clean as the edge of a piece of paper, regardless of how far the surface lay from whatever cast it. Every shadow out there is a cut rather than a gradient, and the unlit side would not be dark in the way a shadow on Earth is dark. Here, shadows are filled with light scattered from the sky, which is why you can see into them easily. There is no sky out there to scatter anything. The only illumination falling into a shadow would be starlight, and the faint reflected light of any nearby surface, and that is all. The contrast between a lit surface and a shadowed one would be far greater than anything in ordinary experience. There is one more property of that light worth mentioning, and it concerns color. The light out there is not different in color from the light here. The sun emits the same distribution of wavelengths, regardless of how far you are from it, so the spectrum arriving at Pluto is identical to the spectrum arriving at Earth, only very much weaker. Any difference in the apparent color of a landscape out there comes entirely from what the surface itself is made of. That matters because human color vision does not work well at low light levels. The cells in the eye responsible for color need a reasonable amount of light to operate, and below a certain threshold they stop contributing and vision becomes effectively monochrome. At Pluto's light level, the eye would be somewhere in the transition. Color perception would be present but weak, washed toward gray, the way colors drain out of a landscape at dusk on Earth. So the honest description of daylight on a Kuiper belt object is this: a landscape lit at twilight levels by a bright star, showing muted color at best, cut by shadows with edges as sharp as blades, under a sky in which the stars never go out. The cold follows the light down, and the cold has a flaw. Part 6. The cold flaw. Temperature in the outer solar system follows a different rule from light, and the difference matters. Brightness falls with the square of distance. Temperature falls with the square root of that, which is to say it falls with the square root of distance. That is a much gentler decline, and it produces a result that seems almost generous at first and then turns out to be the most absolute thing in the region. A body warmed only by sunlight settles at what is called its black body equilibrium temperature. It absorbs energy from the sun and radiates energy away into the dark, and it comes to rest at whatever temperature makes those two rates equal. Around 40 astronomical units from the sun, that balance point sits near 40 Kelvin. Expressed in more familiar terms, that is about 230 degrees below zero on the Celsius scale, or close to 390 below on the Fahrenheit scale. 40 Kelvin is a temperature at which the ordinary categories of matter stop applying. On Earth, we sort substances into solids, liquids, and gases, according to how they behave in a fairly narrow band of temperatures, and almost everything we call a gas is a gas only because our world happens to be warm. Take that warmth away, and the categories rearrange themselves completely. Nitrogen makes the point best, because nitrogen is the most abundant component of the air we breathe, and is a gas in every situation any human being has ever encountered outside a laboratory. Nitrogen freezes solid below about 63 Kelvin. On Pluto, at 40 Kelvin, nitrogen is not a gas and not a liquid. Nitrogen is bedrock. It forms plains hundreds of kilometers across. It flows slowly under its own weight, the way glacial ice flows on Earth, carrying material with it and leaving patterned surfaces behind. It sublimates thinly into a wisp of atmosphere when the world is nearer the sun, and it settles back out as frost when the world moves away again. Methane and carbon monoxide freeze out as well, and they participate in the same slow surface processes. What we would call air, out there, is ground. Water behaves differently again, and its behavior is the reason those worlds have any structure at all. At 40 Kelvin, water ice is not the soft, slippery, easily deformed material we know. It is far below the temperature at which ice creeps, and it has the mechanical properties of rock. Mountains built of water ice stand out there several kilometers high, with steep faces, and they do not slump. They are the bedrock of the outer solar system in the same way granite is the bedrock of continents here, and they will hold their shapes for billions of years because nothing out there is warm enough to soften them, and nothing is close enough to knock them down. Now follow the temperature outward. At 100 astronomical units, the equilibrium temperature has fallen to somewhere near 25 Kelvin. At 1000 astronomical units, it is close to 9. At 10,000, it is approaching 3. And there it stops, because there is a flaw, and the flaw is not set by the sun. The universe as a whole has a temperature. Everywhere in space, arriving from every direction at once, there is a faint background of radiation left over from the beginning of the universe itself, cooled by the expansion of space over billions of years, down to about 2.7 Kelvin. it is extremely weak. But it is inescapable and it is uniform, and it means that no object anywhere can radiate itself colder than that, because the moment it tries, the background warms it back up. This is worth stating carefully, because it is one of the quietly remarkable facts about the far reaches of our own solar system. Somewhere out past a few thousand astronomical units, the Sun stops being the dominant source of heat for the objects that orbit it. The warmth of the universe as a whole takes over. A body drifting in the outer cloud is being kept at its temperature not by the star it belongs to, but by the residual warmth of everything, arriving equally from all sides. The Sun is still there. It is still the object those bodies orbit. It has simply stopped mattering thermally. There is a common misunderstanding about cold in space that should be cleared up before we go on, because it changes the character of everything described so far. Space is not cold in the way a cold room is cold. In a cold room, heat leaves your body quickly because you are surrounded by air that carries it away by contact, and by surfaces that conduct it away where they touch you. Out past Pluto, there is essentially nothing to touch. The only way an object can lose heat is by radiating it, slowly, into the dark. That makes the cold of the outer solar system patient rather than sharp. An object arriving out there warm does not freeze instantly. It cools over a long time, radiating away its heat with nothing to accelerate the process. And it means the temperatures we have been describing are not aggressive. They are simply what everything settles at, given enough time, when there is nothing else to exchange heat with. This is a good place to stop and gather what we have. We began with a boundary that does not exist, a phrase, beyond Pluto, which implies a threshold that nothing has ever crossed because nothing is there to cross. From there we looked at the spacing of the objects and found that the belt everyone pictures as crowded is spread so thinly that the typical distance between neighbors is greater than the distance from here to the Sun. We asked where the rest of the material went and found that it was not missing but relocated, thrown outward by a planet that was itself in motion, leaving behind less than 1% of what the region started with. We looked at the outer boundary of that thinned disk and found a step where a slope should have been, and no settled explanation for it. Then we followed the light down. We found that it fades according to a simple rule, and that it fades past a specific and rather quiet threshold, somewhere near 30 astronomical units, where the Sun stops being a disk and becomes a star. And we found that the same rule, applied twice over, keeps most of the region permanently beyond the reach of any survey. And now the cold, falling more gently than the light, but arriving at something more absolute, a floor set by the temperature of the universe, below which nothing in our solar system or anywhere else can go. 4 kinds of emptiness: spacing, material, light, and heat. Each measured in different units, each falling away at a different rate, and every one of them pointing the same direction. There is one apparent exception to all this cold, and it is worth addressing directly because it changes what the outer solar system might contain. Everything we have said about temperature applies to surfaces, to the outermost layer of a body, in equilibrium with the sunlight falling on it and the darkness it radiates into. Interiors can be different, and for a sufficiently large body they usually are, because there are 2 sources of warmth that have nothing to do with the Sun. The first is radioactive decay. Rock contains small quantities of unstable elements that release heat as they break down, and although the quantity per kilogram is tiny, a body several hundred kilometers across contains a very large number of kilograms and has a relatively small surface through which to lose the resulting heat. Over billions of years, that warmth accumulates. The second is the heat left over from formation itself, released as material fell together and retained in the interior of anything large enough to insulate itself. The consequence is that several of the larger bodies in the outer solar system are thought to have, or to have had, liquid water beneath their surfaces, layers of ocean insulated by a shell of ice, tens or hundreds of kilometers thick, kept from freezing by heat leaking outward from below. The evidence is indirect. Surface features suggesting that material has welled up from underneath, patterns of cracking consistent with a shell resting on something that flows, and in some cases, the shapes the bodies have settled into. This is a genuine qualification to the picture, and it is a pleasant one. The far solar system is not uniformly frozen through. It is frozen at the surface, over interiors that may in several cases be liquid, and the temperature difference across a few tens of kilometers of ice can be 100 degrees or more. But it does not soften the general point, and it is important to be clear about why. Those interior oceans are entirely sealed. Nothing about them reaches the surface in any continuous way. Nothing about them affects the environment above the ice, and nothing about them makes the space between bodies any less cold or any less empty. They are pockets of warmth with no exterior consequence at all, and each of them is separated from the next by hundreds of millions of kilometers of ground that sits at 40 Kelvin or below. If anything, the qualification deepens the theme, rather than relieving it. The only warmth out there is warmth that cannot get out, in interiors nobody has seen, beneath surfaces cold enough that nitrogen is stone. The cold is not merely the dominant condition of the outer solar system. It is the condition that has isolated everything in it from everything else. We are going to keep going outward now, and the emptiness that comes next is stranger, because it stops behaving the way you would expect emptiness to behave. Past a certain distance, the space inside our solar system becomes emptier than the space between the stars. Part 7. The emptiness of the medium. Interplanetary space is not a perfect vacuum, and the thing that fills it comes from the sun. The sun does not only emit light. Its outer atmosphere is so hot that its own gravity cannot hold on to it, and the result is a continuous outward stream of charged particles, mostly protons and electrons, blowing away from the star in every direction at speeds of several hundred kilometers per second. That stream is the solar wind, and it never stops. Near the Earth, the solar wind carries something in the region of 5 particles per cubic centimeter. It is worth pausing on how thin that already is. A cubic centimeter of the air in your lungs contains a number of molecules with 19 digits in it. A cubic centimeter of space near the Earth contains about 5 particles. The space we consider to be well inside the busy part of the solar system is already emptier by a factor no ordinary comparison can carry. The solar wind spreads outward into an ever larger volume, and like the light, it obeys the inverse square law. By the time it reaches Pluto's distance, the density has fallen to a few thousandths of a particle per cubic centimeter. Out past 100 astronomical units, it is thinner still. What that means, expressed the other way around, is that at those distances, you would need to sweep out a volume the size of a small room to collect a handful of particles. Here is a comparison that helps anchor it. The best vacuum that can be created in a laboratory on Earth, using the most capable pumping equipment ever built, in a chamber designed for the purpose, still contains something on the order of 10,000 particles per cubic centimeter. The outer solar system beats it by a factor of millions. No human being has ever built, or is likely ever to build, a volume of nothing as complete as the ordinary condition of space beyond Neptune. That thinning continues outward, and it continues for a long way, but it does not continue forever, and the reason it stops is the most interesting thing in this part of the story. The solar wind is blowing outward into something. The space between the stars is not empty either. It contains its own thin gas, the interstellar medium, and in our particular neighborhood of the galaxy, that gas has a density of roughly 1/10 of an atom per cubic centimeter, along with a magnetic field threading through it. The solar wind, pushing outward, and the interstellar medium, pressing inward, have to reach an accommodation somewhere. They reach it in stages. Somewhere around 80 to 94 astronomical units, the solar wind, which has been traveling supersonically all the way out from the Sun, encounters enough resistance that it slows abruptly. That deceleration front is called the termination shock, and it is a real, physical, detectable structure. 2 spacecraft have passed through it and measured the change. Beyond the shock, the slowed wind continues outward more sluggishly, piling up until it reaches the surface where it can no longer push at all. That surface is the heliopause, and it lies somewhere in the region of 120 astronomical units from the Sun. It is the outer skin of the bubble our star blows in the galaxy, and it is, by the most defensible definition available, where the Sun's physical influence ends. 2 spacecraft have crossed it, and what they measured on the far side is not what anyone would guess. The plasma density went up. Crossing out of the solar system into what everyone calls interstellar space, into the emptiness between the stars, the number of charged particles per unit volume increased by something like a factor of 40. The gas in the space between the stars, in our neighborhood, is roughly 40 times denser than the solar wind is by the time it reaches the boundary. This deserves to be stated as plainly as the arithmetic allows, because it is the sharpest payoff of everything we have discussed tonight. The emptiest region anywhere near us is not the space between the stars. It is the far interior of our own solar system. The Sun spends its entire life blowing a bubble in the galaxy, and the inside of that bubble, swept clean by the outward pressure of the wind, holding nothing but the wind's own thinning remnant, is emptier than the ordinary material of the galaxy it displaces. We live inside a hollow. Not a hollow in a solid thing, but a hollow all the same, held open by a star, and the further out you go inside it, the more complete the hollowing becomes, right up until the moment you leave it and the density goes back up. The crossing itself is worth describing, because it is nothing like the boundary a person would imagine. There was no wall. There was no flash, no shudder, no moment of impact, no change that any camera could have recorded. The spacecraft that made the crossing did not detect it with a camera or a pressure sensor. It detected it as a change in statistics, a shift in the number and origin of the particles blowing past, and a change in the direction of the magnetic field they carried. The most significant border in the entire solar system is registered only as a change in the composition of almost nothing. There is one further property of the boundary region that is beautiful and entirely useless, and it is worth including because it corrects an intuition about what temperature means when there is nothing there. The particles in the region just inside the heliopause are moving extremely fast. Temperature, in the physicist's definition, is a measure of exactly that, the average kinetic energy of the particles in a volume. Apply the definition honestly, and the region has a temperature of somewhere between 30,000 and 50,000 Kelvin. It is, technically, one of the hotter environments in the solar system, and it is sometimes described as a wall of fire. And it does nothing at all. A spacecraft passing through it registers no heating whatsoever, because there are so few particles that the total energy available to transfer is negligible. Fast particles can only warm something if there are enough of them arriving to matter, and out there are not. It is heat without warmth, a temperature with nothing to apply it to. That is a good way to hold the whole idea of the medium out there. Everything about it is real. The wind is real, the shock is real, the boundary is real, the temperature is real. And all of it is spread so thin that none of it has any consequence for anything solid passing through. The far solar system is filled with genuine physics that cannot touch you. 2 spacecraft are out there now, past the boundary, still transmitting, running on the slow decay of a small amount of radioactive material and sending back readings from a region no other object made by human beings has ever occupied. Their signals take the better part of a day to arrive. And the emptiness they are reporting from is, by every measure we have, more complete than the emptiness they are heading into. The shape of that bubble is worth describing, because it is not the sphere that the word suggests. The sun is moving. It travels through the local neighborhood of the galaxy at something like 20 kilometers per second relative to the gas around it, and the interstellar medium therefore does not press on the heliosphere evenly. It presses harder on the leading side. The result is a structure elongated in the direction of travel, compressed at the front, where the wind meets the oncoming gas at around 120 astronomical units, and drawn out behind into a long trailing region that may extend several times further before it disperses. We have measurements from the leading side, because both spacecraft that have crossed the boundary happen to be traveling in roughly that direction. The trailing side has never been visited and is not well constrained. Whether it ends in a definite surface or simply frays out over a great distance into the surrounding gas is not settled, and there is not much prospect of settling it by direct measurement in any foreseeable time. There is a second function of the bubble that deserves mention, because it is one of the few ways the outer solar system reaches into daily life on Earth. The galaxy is filled with cosmic rays, atomic nuclei accelerated to enormous energies by distant violent events, arriving from every direction at all times. The heliosphere partially blocks them. The outward flowing wind and the magnetic field it carries deflect a substantial fraction of the lower energy cosmic rays before they can penetrate to the inner solar system. Measurements taken from beyond the boundary confirm this directly. The cosmic ray intensity out there is considerably higher than it is here. That shielding is not constant. The sun's activity rises and falls over a cycle of about 11 years, and when activity is high, the wind is stronger, and the shielding is more effective, and fewer cosmic rays reach the inner planets. When activity is low, the bubble weakens slightly, and more get through. The variation is measurable in the upper atmosphere of the Earth, and it is recorded over long spans in the chemistry of ice cores and tree rings. So the emptiness we have been describing is not entirely without effect. The most hollowed-out region anywhere near us is hollowed out by a wind that also happens to be holding back a portion of the radiation of the galaxy, and the strength of that protection varies with the mood of the star at the center. It is a strange arrangement to hold in mind. A bubble of near-perfect nothing, extending 120 astronomical units in one direction and further in the other, blown continuously by a star, doing almost nothing to anything solid that passes through it, and quietly shielding every world inside it from a fraction of what the galaxy is throwing. Which brings us to the emptiness that is hardest to feel from here, because it is not made of space at all. Part 8. Slow time. The emptiness beyond Pluto is also an emptiness of events, and this is the kind that is hardest to picture from a world where things happen constantly. Out there, almost nothing happens, and the reason is not a lack of physics. The reason is that everything moves too slowly for the physics to produce results within any span a human being can hold in mind. Orbital speed falls with distance from the Sun, because the further out a body is, the weaker the gravitational pull holding it, and the slower it needs to move to stay on its path. The Earth travels around the Sun at about 30 kilometers per second. That is fast enough to cross a continent in a couple of minutes. Jupiter manages about 13. Neptune, about 5.5. Pluto, less than 5. The periods stretch accordingly. Pluto takes about 248 years to complete one orbit. Set that against the span of human attention, and it produces a fact worth stating carefully. Pluto has not completed a single orbit since it was first identified. Everyone who has ever observed it, every measurement ever taken of it, Every image ever returned from it covers a fraction of one circuit. We have watched roughly a third of one Plutonian year, and no living person will see that year completed. Further out, the slowing becomes extreme, and it becomes most extreme at the far end of an elongated orbit. A body on an ellipse moves fastest at its closest approach to the Sun and slowest at its furthest point, which astronomers call aphelion. For an orbit that is only slightly elliptical, the difference is modest. For the orbits out here, which are elongated to a degree the inner solar system never produces, the difference is enormous. There is a well-known detached object whose orbit illustrates this better than any description. Its closest approach to the Sun is around 76 astronomical units, already almost twice as far out as Pluto ever goes, and far enough that Neptune has no meaningful influence on it. Its furthest point is many hundreds of astronomical units beyond that. One complete orbit takes something over 11,000 years. At the far end of that orbit, it is barely moving. Its speed at aphelion falls to a small fraction of a kilometer per second, which puts it in a range that ordinary vehicles on Earth can match. A body several hundred kilometers across, made of ancient ice, drifting through the dark at a speed a fast car could keep pace with, several hundred times further from the Sun than we are, for thousands of years at a stretch. And that object is not the extreme case. It is simply one that has been found. Objects belonging to the outer cloud further out have periods measured in millions of years. A body released from the outer regions and falling inward on a long orbit takes a substantial fraction of 1,000,000 years to arrive. It begins the journey before anything recognizably human exists and completes it a long time afterward, and for the overwhelming majority of that journey, it is moving so slowly that a photograph taken a century apart would show no change worth measuring. The consequences of this slowness are the reason the outer solar system is what it is. Consider collisions. Two objects meeting at 30 kilometers per second destroy each other. Two objects meeting at a few meters per second do not. Out beyond Pluto, the relative speeds between neighboring bodies are so low that a collision, in the rare event of one, is not an impact in the sense we usually mean. It is a contact. Nothing out there is being ground down. Nothing is being shattered and reaccumulated. The population of objects is not the wreckage of a more numerous earlier population, the way much of the asteroid belt is. It is largely the original material, in something close to its original form. Consider erosion. There is no atmosphere to weather a surface, no water to move sediment, no tectonic activity on bodies that small and that cold, and almost no impacts to churn the ground. Sunlight is a millionth of what it is here and does very little. Cosmic rays and the slow drizzle of charged particles do the only real work, and what they do is chemical rather than mechanical. They darken and redden the ices over hundreds of millions of years by splitting simple molecules apart and letting the fragments recombine into heavier organic compounds. That is why so many of these bodies are deep red. It is the only weathering available. Consider change of any kind. A landscape out there is not old in the way a mountain range on Earth is old. An old mountain range has been built and worn down and built again. A surface in the Kuiper belt has been sitting untouched since it formed. The distinction matters. The material is not ancient and altered. It is ancient and unaltered, and it is the closest thing available to a direct sample of the conditions in which the solar system was assembled. There is a version of this slowness that applies to us as well, and it concerns how anything is learned about the region at all. A signal from the outermost operating spacecraft takes the better part of a day to reach the Earth. That means every measurement ever made of the far solar system arrived after the fact, and always will. It is a small thing, and it is permanent. There is no possible technology that removes it, because the delay is not a limitation of the equipment. It is the speed of light applied to a distance that is genuinely that large. And there is a further consequence of the slowness that shapes what we can know. Objects on very long orbits are detectable only during the small portion of each circuit when they come near enough to reflect a usable amount of sunlight. For an object with an 11,000-year period, that window might be a few centuries. For an object with a million-year period, the window is a similarly small fraction of a much longer time, which means that the population of the outer solar system is being sampled through a very narrow slot. We are seeing the small minority of distant objects that happen, right now, in this particular century, to be at the near ends of their orbits. All the others are out at the far ends, moving at walking pace through the dark, entirely undetectable and entirely there. There is a way to hold all of this that turns it from a description of absence into something more comfortable, and it is worth arriving at before we go further out. Nothing out there is in motion toward anything. The slowness that makes the region unobservable is the same slowness that has kept it intact. Nothing has been broken because nothing was moving fast enough to break it. Nothing has been worn away because nothing was there to do the wearing. The emptiness and the stillness and the preservation are not three separate facts. They are one fact, seen from three directions. The slowness has one further dimension that is worth drawing out, because it applies to rotation as well as to orbits, and it produces some of the strangest arrangements in the solar system. Bodies out there are not being tidally worked on by anything. In the inner solar system, tides are constantly at work. The moon has been slowed until it keeps one face permanently toward the Earth, and the Earth itself is being slowed by the moon in return, at a rate that lengthens our day by a small fraction of a second each century. Those effects require proximity, because tidal forces fall off extremely steeply with distance. Out past Pluto, there is nothing close enough for tides to matter, except within the small number of systems where a body has a companion of its own. And a surprising number of them do. Binary systems are common in the Kuiper belt, pairs of objects orbiting one another, often of comparable size, often widely separated, moving around their common center with periods of days or weeks. Those pairs are informative, and what they tell us reinforces everything else in this part. A widely separated binary is a fragile arrangement. The two components are held together by their own weak gravity, and almost any disturbance would break the pair apart, a close pass by a third object, a collision, a strong gravitational encounter of any kind. The fact that so many of these pairs still exist, after 4.5 billion years, is direct evidence that they have not been disturbed. They are a measurement of how little has happened out there, expressed in the survival of things that could not have survived anywhere busier. The same logic applies at a larger scale to the classical objects generally. Their orbits are close to circular and close to the original plane. Circular, uninclined orbits are what an undisturbed population looks like. Anything that had been scattered or repeatedly perturbed or worked on by a passing mass would show it in the shape and tilt of its path. Much of the classical belt shows nothing of the kind. So the record out there is legible in a way that records rarely are. In most of the solar system, the past has been overwritten, surfaces resurfaced, orbits shuffled, small bodies broken up and their fragments redistributed. Beyond Pluto, very little has been overwritten, because the writing implements were removed early and never came back. That is what the slowness has brought. Not merely a region where nothing happens now, but a region that has preserved a readable account of what happened once, 4.5 billion years ago, in the orbits of pairs of objects too loosely bound to have survived being touched. And it is that stillness that produced the one thing out there we have managed to look at closely. Part 9. What was actually found out there? After a great deal of absence, it is worth spending some time on the one solid thing that has been examined closely in that region, because the story of how it was found says more about the emptiness than any measurement of it, and because what it turned out to be is unexpectedly gentle. The spacecraft that flew past Pluto was still healthy when it left. It had fuel remaining, it had working instruments, and it was traveling outward on a trajectory that would take it deeper into the Kuiper belt. The obvious thing to do was to fly it past something else. There was one difficulty. The spacecraft could only change direction by a very small amount, which meant the second target had to lie within a narrow cone of space directly ahead of it, and nobody knew whether anything did. So a search was mounted. Large telescopes on the ground were pointed into that cone and swept it repeatedly, looking for anything faint and slow-moving in the right part of the sky. The search ran for years. It found nothing usable. The region ahead of the spacecraft appeared, as far as the most capable ground-based instruments could determine, to contain nothing at all. Eventually, a space telescope was turned to the problem, an instrument in high demand, allocated in small increments, pointed at a small patch of sky in the hope of finding a body a few tens of kilometers across, at a distance of more than 6 billion kilometers. It found one. It found exactly one, and that one was reachable only just, requiring most of the maneuvering fuel the spacecraft had left. It is important to understand what that search result actually means, because it is easy to read it as a story about the difficulty of astronomy. It is not. The telescopes involved were more than capable of detecting objects of that size at that distance. The search was hard because there was almost nothing to find. In the entire volume of space that the spacecraft could still reach, across a region tens of millions of kilometers wide and hundreds of millions long, there was one object. Not one interesting object. One object. That is the emptiness we have been describing, expressed as a practical problem rather than a number, and it is probably the most convincing form the number ever takes. The object it reached lies at about 44 astronomical units from the Sun, and it turned out to be two bodies gently joined together. It is a contact binary, two separate objects resting against one another and held there by their own weak gravity. End to end, it measures something like 35 kilometers, which is to say roughly the size of a large city. Both lobes are flattened, more like two smooth pebbles than two spheres, and they meet along a narrow neck. Its surface is deep red, the color built up over billions of years by weak radiation working slowly on simple ices, splitting methane and other light molecules apart and letting the pieces recombine into heavier organic compounds. That reddening is the only process that has happened to it since it formed. It is old in exactly the way we described in the last part, old and unaltered. But the most important measurement was not the color or the size. It was the joining. The two lobes did not crash together. If they had, the geometry would show it. A high-speed impact leaves a crater or shatters both bodies, or produces a compressed and deformed contact zone with fractures radiating away from it. None of that is present. The neck between the two lobes is clean. The lobes retain their original shapes almost perfectly, right up to the surfaces where they touch. Working backward from that geometry gives a merger speed of a few meters per second, slower than walking pace. Two objects the size of cities, made of ancient ice, drifted toward one another across the dark for however long it took, made contact at the speed of a person crossing a room, and stopped there. They have been resting against one another ever since, for something over 4 billion years, and nothing has come near enough to disturb the arrangement. This is the quiet reward at the center of the whole evening, and it is worth sitting with. Out where things are furthest apart, the few things that do meet gently. There was never enough speed out there for violence. The same emptiness that makes the region so difficult to observe and so difficult to reach and so nearly impossible to map is also the reason that the one object we have looked at closely turned out to be two things resting quietly together rather than the fragments of a collision. The formation of that object also tells us something about how the region was built. Slow accretion at a few meters per second is not a rare accident. It appears to be how bodies out there generally came together, not by violent impacts building up a mass, but by material drifting into loose contact and simply staying. The Kuiper belt was not hammered into existence. It settled. The region receives occasional visitors as well, and they are worth mentioning, because they say something about what lies beyond it. Objects have now been observed passing through the solar system on unbound paths, arriving from the direction of another star, crossing the inner regions once and departing without ever being captured. Their trajectories are not ellipses. They are open curves, and an open curve means the object was never in orbit around our Sun at all. More than one such visitor has now been seen. The existence of those objects tells us that interstellar space carries a population of free-floating bodies, thrown out of other star systems by processes very much like the one that emptied our own outer disk. And the rarity of the sightings tells us how thinly that population is spread. These are objects we can only detect when they come close, and we have been watching carefully for a while now, and we have seen a small number. There is a symmetry there worth noticing. The material that Neptune threw out of our own outer disk 4.5 billion years ago went somewhere. Some of it is still loosely bound to the Sun in the outer cloud. Some of it left entirely and is now drifting between the stars, and will occasionally pass through another solar system as a brief, unexplained visitor of exactly this kind. Which means that the emptiness we have been describing is not local. It is the general condition, produced everywhere by the same processes, and our particular hollow is one of many. The encounter itself deserves a moment, because the conditions under which it was carried out say as much about the emptiness as the object did. The spacecraft had no ability to stop, or to slow down, or to go back. It was traveling at something over 14 kilometers per second, and the target was roughly 35 kilometers long. The entire close approach, the portion of the flight during which the object was near enough to be resolved into anything more than a point, lasted a matter of hours, and the closest and most detailed part of it lasted minutes. Everything had to be planned in advance and stored on board, because at that distance, a signal takes 6 hours in each direction, and there is no possibility of correcting anything in real time. The instructions were written, uploaded, and then executed by a machine 6 billion kilometers away, entirely alone, pointing its instruments at a body whose position was known only approximately and whose shape and rotation were not known at all. There is one detail of that operation that is quietly remarkable. In order to point accurately enough, the navigation team had to know where the object was too within a few tens of kilometers, at a distance where a small angular error corresponds to an enormous positional one. They refined that knowledge in part by watching the object pass in front of background stars, brief events lasting a second or two, observed from portable telescopes carried to remote locations, timed precisely enough to constrain the object's position and rough outline before anything had ever seen it as more than a moving point. And then, after the encounter, the data had to come home. The full set of observations, images, spectra, particle measurements, took well over a year to transmit, because the available bandwidth at that distance amounts to a trickle. The information arrived slowly, a fragment at a time, for months after the event it described was over. Everything about that operation was shaped by the emptiness. The single available target, the one chance to pass it, the 6-hour delay, the year of downloading. None of it is a limitation of engineering in any straightforward sense. All of it follows from the distances involved and from the fact that there was, in that entire volume of space, almost nothing to go and look at. It is the most thorough examination anyone has made of anything beyond Pluto. It amounts to a few hours of close observation of one object out of 100,000 in a region that extends for tens of thousands of astronomical units beyond it. That is the sum total of what has been examined at close range in the outer solar system, and it is not likely to be added to for a long while. And past the outermost objects that Neptune could ever have touched, there is a population that Neptune cannot explain at all. Part 10. The detached ones. Beyond the scattered disk, there are objects that do not fit any of the accounts we have built so far, and the way they fail to fit is specific and instructive. Every population we have discussed tonight can be traced back to Neptune. The Plutinos and the other resonant bodies were captured by Neptune's migrating resonances. The classical objects sit in a region Neptune's influence reaches, and their orbits reflect it. The scattered disk was thrown by Neptune and remains loosely under its authority, returning to Neptune's neighborhood at the near end of every long circuit and receiving another small adjustment each time. The detached objects do none of this. Their closest approach to the Sun is far outside Neptune's reach, 76 astronomical units in the best-known case, and comparable or greater for the others. At that distance, Neptune's gravitational influence is far too weak to have placed them where they are. They never come close enough for Neptune to have thrown them, and they never come close enough for Neptune to be adjusting them now. They are, as the name says, detached, separated from the machinery that governs everything else out there. Which raises an obvious question. Something moved them onto those orbits. Whatever it was, it is not doing so any longer, because nothing currently in the solar system can reach them. The candidate explanations are all still live, and they divide into two families depending on whether the cause was inside or outside the solar system. The first family looks outward, to the Sun's early environment. As we discussed with the Kuiper cliff, the Sun almost certainly formed inside a cluster of young stars, and during those first tens of millions of years, other stars passed far closer than any star has passed since. A close passage does not only strip material away, it can also lift the near points of orbits, taking a body that was thrown outward by a planet on a long ellipse and raising its closest approach so that it no longer returns to the region it came from. That is precisely the signature the detached objects show. They look like scattered disk objects whose near ends were lifted out of Neptune's reach and left there. In this account, they were placed by a star that drifted away 4.5 billion years ago and has been elsewhere in the galaxy ever since. The arrangement we observe is a record of an event whose cause is no longer present and never will be again. The second family looks inward, to something still in the solar system, or something that used to be. A body of substantial mass on a distant orbit could produce the same lifting effect, and could still be doing so. Alternatively, a large body could have been present early on, done this work, and then been ejected, leaving the orbits it shaped behind as evidence of its former presence. There is an observation that keeps this second family alive, and it needs to be presented carefully because it is often reported without its limitations attached. Among the most distant of these objects, the orbits appear to be grouped. Their long axes lean in a broadly similar direction, and the planes they orbit in are tilted in a broadly similar way. A population placed by many independent random events should show no such preference. Orientations should be scattered evenly around the sky. They do not appear to be. If that grouping is real, something is maintaining it, and the most direct explanation is the gravity of a substantial undiscovered body on a distant orbit, shepherding those orientations the way a planet shepherds a resonance. Now the limitations, which deserve exactly as much weight. These objects are discovered only when they are near the closest points of their orbits, because that is the only time they are bright enough to detect. They are also discovered only in the patches of sky that surveys actually covered, at the times those surveys ran, under the conditions that prevailed. Both of those constraints introduce preferences into the sample that have nothing to do with the real distribution. A grouping in the discovered objects can be produced by a grouping in where and when people looked. There is also a possibility that requires no single large body at all. If the outer solar system contains a substantial disk of small objects, too faint individually to detect, but massive collectively, the combined gravity of that disk could produce the same shepherding effect without any planet being involved. And there is the plainest limitation of all. The number of objects showing this grouping is small. It is small enough that the pattern's significance depends heavily on how the statistics are handled, and reasonable people handle them differently. None of this should be framed as a hidden answer or a suppressed discovery. It is an open observational question about a region we have barely begun to sample, and the honest position is that too few objects have been found to settle it. Searches continue, and new survey instruments are now coming into operation that will cover far more sky, far more sensitively than anything before them. The question may well be answered within a few decades, in one direction or the other, and either answer would be interesting. What matters for tonight is what these objects mark. They are the first bodies belonging to our solar system whose orbits are governed less by our planets than by things outside it, by stars that passed long ago, or by the general pull of the galaxy, or by something we have not yet seen. They sit at the transition between a solar system that is organized and a solar system that is merely gathered. It is worth stepping through what a search for something like this actually involves, because the difficulty explains why the question has stayed open for as long as it has. A substantial body on a very distant orbit would be faint for all the reasons we established earlier. It shines only by reflected sunlight. It is subject to the fourth power penalty, and if it lies several hundred astronomical units out, it could be many thousands of times fainter than the objects that current surveys routinely detect. Depending on its size, its composition, and how reflective its surface is, it might sit at the very limit of what the largest telescopes can reach, or somewhat beyond it. It would also move extremely slowly. The detection technique we described earlier relies on catching motion between exposures, and a body at several hundred astronomical units drifts so little from one night to the next that separating its motion from measurement noise becomes genuinely difficult. The method that works well for the Kuiper belt works poorly at the distances in question. And there is the matter of where to look. If the grouping of the known detached orbits is real, it constrains roughly where such a body would have to be, but only roughly. The region indicated still covers a substantial area of sky, and much of it lies in directions crowded with the stars of the Milky Way, where a faint, slow-moving point is hardest of all to pick out against the background. A new generation of survey instruments is now beginning operation, designed to image the entire visible sky repeatedly over a period of years, at sensitivities well beyond anything previously sustained across that much area. That approach is well suited to the problem because it removes the need to guess where to point, and it builds up the long baselines that slow motion requires. Within a decade or so, the searchers will either find something or will have covered enough of the possible range to make its absence meaningful. Both outcomes would be worth having. A discovery would rewrite the architecture of the outer solar system and would immediately explain several things that are currently unexplained. A confident absence would push the interpretation toward the other candidates, the passing star, the massive distant disk, or the observational preferences of the surveys themselves, and would be nearly as informative. What should not be lost in either case is the state we are actually in, which is a good and honest one. We have a region of our own solar system large enough to hold everything we know several thousand times over, sampled at a handful of points, containing objects whose orbits record events we cannot reconstruct. Not knowing is the appropriate condition. It reflects how much of the region remains unexamined. And past them, the organization gives out entirely. Part 11, where the sun lets go. The outermost part of the solar system is not shaped like the rest of it, and the difference in shape is the first thing to understand about it. Everything we have discussed so far lies in or near a plane. The planets orbit in a flat disk. The Kuiper belt is a thickened version of that same disk. Even the scattered objects, tilted as they are, still bear the mark of having been thrown from something flat. The Oort cloud is not like this. It is a shell, a roughly spherical distribution of icy bodies surrounding the entire solar system in every direction at once, including straight up out of the planetary plane and straight down beneath it. The reason for that shape follows directly from what we established several parts ago. The material out there was thrown, hard, by the giant planets during the early migration. Once an object is thrown far enough that the sun's hold on it becomes weak, it stops belonging to the plane it came from. Passing stars and the general pull of the galaxy work on it over hundreds of millions of years, tilting its orbit, until the population that started as a flat disk has been stirred into a sphere. The inner region of that shell is usually placed at a few thousand astronomical units from the Sun. The outer reaches extend to somewhere in the region of 50,000 to 100,000 astronomical units, which is approaching 1 light-year, a meaningful fraction of the distance to the nearest star. The population is thought to be enormous. Estimates commonly run to something like 1 trillion objects a kilometer across, or larger. And now apply the lesson of the second part of tonight, because it applies here more forcefully than anywhere. 1 trillion objects sounds like a crowd. Spread through a spherical volume approaching a light-year in radius, the typical separation between neighbouring bodies works out to something on the order of tens of millions of kilometres, comparable to the distance between the Earth and Venus at their closest approach. From the surface of an Oort cloud object, the Oort cloud is invisible. Again, at 1,000 times the distance, the same thing is true, and it is true more completely. The total mass is small. Estimates carry very large uncertainties, but they generally amount to a few Earth masses at most. 1 trillion objects, distributed across a sphere nearly 2 light-years across, weighing altogether less than a small handful of planets. That is the final form of the emptiness we have been following all evening. Now the sky from out there. At 50,000 astronomical units, the Sun has faded to roughly the brightness that Venus reaches from Earth. It is unmistakable. It is the brightest point in the sky by a comfortable margin, bright enough to cast the faintest suggestion of a shadow, and it would be the obvious first thing anyone would notice. And it is unmistakably a point. It has been a point since 30 astronomical units, and out here, it is a point that has faded into the general population of bright stars without ever ceasing to be the one that matters. Everything else about that sky is unchanged. The constellations look exactly as they look from Earth. 50,000 astronomical units is an enormous distance by the standards of a solar system and a negligible one by the standards of the galaxy, so the patterns of stars have not shifted in any way an eye could detect. You could travel out there, across a distance that would take a spacecraft tens of thousands of years, and find the sky above you identical in every respect but one. One star would be brighter than it used to be. That star is the Sun, and this is still, technically, home. Out there, the Sun's grip has become weak enough that other things compete with it, and this is where the solar system stops being a system in any strict sense. The first competitor is the galaxy itself. The Milky Way pulls on the outer cloud, and because the cloud is so large, the galaxy's pull is very slightly different at one edge of it than at the other. That difference is a tide, in exactly the sense that the moon raises tides in our oceans, and out at those distances the galactic tide is strong enough to reshape orbits over time. Bodies are slowly lifted and lowered, their near points raised and dropped by the accumulated pull of 100 billion distant stars. The second competitor is those stars individually. Over the age of the solar system, stars have passed within a light year or two of the Sun many times, and they continue to do so every few 100,000 years. A star passing at that distance does not disturb the planets in the slightest. But it moves through the outer cloud, and it can pull objects out of it entirely, or push them onto new paths, or nudge one of them onto an orbit that falls inward. That last effect is the one we occasionally see the result of. The comets that arrive in the inner solar system on very long orbits, appearing once and then departing for tens of thousands of years or longer, are the outcome of exactly this process. Some object far out in the cloud was pushed, by the galactic tide or by a star drifting past, onto a path angled slightly more toward the Sun. Then it fell inward for 1,000,000 years or more, gathering speed very gradually, and arrived here to be seen briefly by whoever happened to be looking. Which returns us to the question we started with, and lets us answer it properly. Where does the solar system end? It does not. The Sun's gravitational authority does not stop at any surface. It fades across the whole width of the outer cloud, and somewhere in the region of 1 to 2 light-years, it becomes comparable to the pull of the galaxy at large. The objects out there at that transition are not clearly the Sun's, and not clearly anyone else's. They are held loosely enough that a passing star can take them, and they have been taken, and given, and exchanged for 4.5 billion years. There is no wall. There never was. The phrase beyond Pluto describes a direction along which everything thins. The objects, the light, the heat, the medium, the speed, the number of things that happen, and continues thinning without limit until it becomes indistinguishable from the space between stars. And now hold all of it at once, in the form we started with. A dark body of ancient ice, somewhere out in the outer shell. Underfoot, a surface of nitrogen and water ice at 3 degrees above absolute zero, unchanged for longer than the Earth has had continents. Overhead, an unbroken field of stars, in the familiar patterns, present at all hours because there is no atmosphere and no daytime and nothing to wash them out. Among them, one point of light a little brighter than the rest. Nothing is nearby. Nothing is approaching. The next object of any size is tens of millions of kilometers away and is moving no faster than you are. The last time anything came close enough to matter, a star passed by, and that was a very long time ago, and the next time will be a very long time from now. There is a final piece of arithmetic that puts the whole outer solar system in proportion, and it is best done with travel times rather than distances. The fastest spacecraft ever sent outward from the Earth reached Pluto in 9.5 years. Those same spacecraft, continuing at their present speeds, would reach the heliopause at around 120 astronomical units after something over 30 years of flight. That is a journey within a human career, and it has been accomplished more than once. Now, extend it. At those speeds, the inner edge of the outer cloud, a few thousand astronomical units out, lies roughly 300 years ahead. Not 300 years of planning and construction, 300 years of flight, after launch, with everything already working. The far reaches of that cloud, at 50,000 astronomical units, lie something on the order of 10,000 years further still. A spacecraft launched at the beginning of recorded human history, on the fastest trajectory we currently know how to produce, would still be inside our own solar system today, and would still have a considerable distance to go before leaving it. That is the true depth of the region, and it is worth holding beside the nearest star. The nearest star sits at about 268,000 astronomical units, a little over 4 light-years. Which means that the outer cloud, at its furthest, extends something like a fifth of the way there. The solar system does not merely have a large outer region. Its outer region occupies a substantial fraction of the distance between stars, and the gap between our cloud and whatever equivalent structure surrounds the next star along may be smaller than the cloud itself. There is a consequence of that worth stating plainly. It is entirely possible that the outer reaches of our Sun's cloud and the outer reaches of a neighbouring star's cloud are not separated by anything much at all, that the boundary between one solar system and the next is not a gap, but a region of overlap, where objects are held so weakly that which star they belong to is a question without a firm answer. Which is where the phrase we started with finally comes apart entirely. Beyond Pluto is not the beginning of the space outside the solar system. It is the beginning of the largest part of the solar system, a part that comprises almost all of its volume, contains almost all of its objects by number, and has been visited at exactly one location by exactly one machine, briefly, on its way through. Everything anyone has ever seen closely of the outer solar system amounts to a few hours of photographs of a single body resting quietly against another. We began by calling this emptiness worse than you think, and by every measurement we have taken tonight it is. It is emptier than the illustrations, emptier than the models, emptier than the space between the stars, and it never resolves into anything less empty no matter how far out you go. But every one of those measurements has also turned out to describe something else. Nothing is broken out there because nothing was moving fast enough to break it. Nothing has been worn away because nothing was close enough to wear it. The two objects we found resting against one another have been resting for 4 billion years, and they will still be resting long after every question we have asked tonight has been answered or forgotten. And so the far solar system stays as it has always been, too spread out for anything to meet, too dim for anything to hurry, too cold for anything to change. It is not waiting for us, and it is not troubled by us, and it will still be exactly this quiet, long after tonight has been forgotten. Let your breathing slow. Let the dark grow soft and wide around you. Sleep well, and good night.